Welcome to the CBER Symposium on DeFi, which is moderated by the great work and talks of Professors Cam Harvey, David Yermak, Gur Huberman, and Bruno Bie, and the recent working papers of Professors Christian Parlor and Agostino Caponi on the decentralized exchange. Let me also thank Will and Fahad for their kind invitation to me and Julian to host this session, and the three speakers and their co-authors that accepted to be with us today. The first author is Arthur, who will be talking about quantifying blockchain extractable value. How dark is the forest? So Arthur, please start sharing your screen, and the screen is yours.
Thank you very much for the kind introduction. Can everybody hear me loud and clear and see my screen?
Yes.
Yeah. Okay, great. So many of you are probably already familiar with what DeFi is. I would just give you a very brief map of all the services that you can expect. I mean, not all of the services, but most of the services. And obviously, on a daily basis, we have new emerging ideas and projects coming about, which makes the space so exciting. So at the heart, we have this distributed database, which is a blockchain. This itself is divided into various layers. So for example, we have here the P2P network layer, then the consensus layer, and then an application layer where developers can develop DeFi applications. So out of this, or from this base, we have seen like a plethora of various protocols emerging. For example, exchanges, lending and borrowing platforms, novel constructs such as flash loans. And this economic environment has quickly gathered or attracted various players that are performing or that are acting in different ways on the market. So we can, for example, we can see a variety of arbitrageurs, people that are doing liquidations if a loan gets liquidated, or debt collateral of a loan gets liquidated. We do have various players voting on proposals, etc. The beauty of DeFi, I think, is mostly attributable due to the really key asset standards that are being accepted like almost across the entire industry. So we have a native coin, then we have fungible tokens, and we have non-fungible tokens, and they often follow certain standards so that protocols can be composable, which is really key. So what is blockchain, or if you want to call it miner extractable value, MEV or BEV? So just give you a very small example. So for example, if you have a lending protocol, right, where you can borrow and lend assets, then what you can do is you can borrow, so you can collateralize, for example, Ether into a liquidity pool. Then you borrow some assets. For example, you can mint DAI, right? That would be the example of MakerDAO. And then if the price of Ether, so the price of your collateral, drops below a certain threshold, and the technical term would be if it drops below a health factor, right? Here then, in that case, your collateral, which is Ether, can be opened up for liquidation. So it's basically the smart contract decides from now on, anyone can jump in and can repay the debt in order to claim the collateral with a bonus, at a discount. And this is often referred to as the liquidation spread. So you have the bonus of the collateral. So you have the actual price, and then you have a bonus. So, for example, 5%, 15% bonus that you receive on top of the market price, let's say, in order to repay this collateral, repay the debt, and get the and receive the collateral at a discount. So liquidation is an example of miner extractable value because we have the question of who will actually execute this liquidation. Right? So any idea? Here in the forum, any idea who would perform a liquidation? who are the various actors that might have a privilege to perform liquidation? Is it anyone? And who is anyone? Any idea? Exactly. For example, yeah, exactly. For example, a miner might do this, right? So a miner here might be an entity who liquidates, but it can also be just you, right? Even if you're not a miner, you can just create a transaction and repay debt from someone else that you have never encountered in your life, but you think this is a good financial step to perform. And it can also be so-called front runners, so people that are trying to front run others because they act maybe a bit later. You can call them adversary, you can call them just liquidators. That really anyone can do this. So what are we talking about? Is MEV a big thing? BEV, is this significant? Well, we performed an empirical study over 32 months, and we found like a bit more than $500 million in profit over these 2.5 years. And this is only on the Ethereum blockchain. So in order to quantify this number, we devised a variety of heuristics, which may very well have some false positives, but we try to keep them, let's say, as tight as possible. So we don't have a significant ground truth data, for example, for certain types of MEV, as I will discuss a bit later. But for example, for liquidations, it's rather simple. It's quite obvious. You can very clearly pinpoint how much profit was made in a liquidation attempt. So what is our data set? Well, we just use the public Ethereum blockchain, right? There's nothing hidden about this data set. You can go and crawl the Ethereum blockchain yourself. That's the same database that we had access to, and just apply the heuristics that we described, for example, in our paper. And hopefully you find the same results, unless we have some bugs in our code. But just to give you some numbers, so we have about 11,000 unique addresses that we identified in BAV, roughly 50,000 cryptocurrencies that we capture, and 60,000 on-chain markets. So an on-chain market is typically a liquidity pool where there are two assets in this liquidity pool, or at least two assets in this liquidity pool. So we try to have quite a comprehensive understanding of DeFi by capturing as many cryptocurrencies as possible. And we noticed that in particular, smaller liquidity coins actually do matter significantly for MEV. So if we only consider like the top 100 cryptocurrencies, we wouldn't capture that much MEV. Great, I see some questions in the chat. I guess this includes front running on Uniswap and friends as well. Yes, exactly. It does include front running. So it's good that you asked this question. I will actually, in the next part of the talk, I will discuss the sources of MEV that we measured. So mostly these are three sources: sandwich attacks, liquidations, and arbitrage. Before jumping there, I wanted to briefly mention Flashbots, because they have also performed quite a nice empirical study on how much MEV is extracted. So this is like a project from the practitioners community. So feel free to also explore their data, their metrics, and you can contrast them to academic works. I think it's always great to have various sources that tell you how much MEV or BEV people estimate there to be. All right, so before diving into sandwich attacks, which I would like to explore and explain a little bit, I will give a very brief background on automated market makers, or also called AMMs. So an AMM, in essence, is an idea where you use a smart contract to perform market making. Market making is the process of serving liquidity to a market by either adding bids or asks in a limit order book in a traditional setting, or by in a DeFi setting or AMM setting. It's simply the smart contract doing the market making autonomously. So you do have a constant product formula. So you have a quantity of an asset X and a quantity of an asset Y. And the sum, the product of both should be equivalent to a constant while you do trade with the liquidity pool. So this allows you to get access to instant liquidity irrespective of the trade size. So it's certainly a good thing. However, you have a certain slippage, right? So the price of the exchange changes the more liquidity you kind of request from the liquidity pool. So naturally, a purchase of an asset X increases the price of X and decreases the price of the other asset Y. So the ratio between X and Y sets the price, or sets the spot, if you want to call it the spot price. And such a AMM is also known as constant product AMM. There may be other variations and formulas that you can find in the literature. So to give you a concrete example, here we have on the x-axis the amount X of asset capital X. So that's one asset in the pool, and we have another asset in the pool, which is Y. Here, this line that you see, this is the bonding curve that is basically governing the exchange of assets in this liquidity pool. And let's say at the beginning, we have here this first state where we have X is equal to 10 and Y is equal to 30. So the K, the constant of this AMM, is 300. Now, if we want to remove some liquidity here, right? If we want to get, let's say we want to remove, I think it is, let's say 10 coins here. So to 20 here. How much of Y do we have to provide to the pool? So if we want to receive 20 units of asset Y, how many units of asset X do we have to provide to the pool? Can anyone give me a hint? $15. Perfect. Very good. So exactly, right? So we want to keep the K, the constant, right? So in order to receive here 10 coins out of the pool, we have to provide +5 here, right? I mean, we go to 50. This is the correct answer, right? Okay, good. So the expected slippage of a liquidity pool is really this change in price if you move along this bonding curve. And this you can calculate because you know the state before and you know the state after of the exchange, right? So based on the trade size that you would like to enact, you can calculate the expected slippage. Now, due to the asynchronicity of blockchain networks, you're not precisely certain at which state your trade transaction will execute. So the state of the AMM might change before your transaction gets executed. So your estimation of the slippage may be wrong. And that's called the unexpected slippage. So because you're uncertain about it. And this unexpected slippage can go either in your favor or against your favor. So you can get a worse execution price, as you can see in this slide, or you can get a favorable execution price if there's another, like a contrary trade executing before your trade. So I hope you get a bit of the idea of how to jungle with this bonding curve. There's one more little net that we would like to look at, and that's the slippage protection. So because you don't really know how far the slippage can get, you can set a deadline or like a limit in a sense. It's quite similar to a limit order. You don't want to basically go beyond this price. So if the unexpected slippage would push you beyond that slippage protection, your transaction will fail. So if it fails, you still have to pay some transaction fees to the chain, but they won't be that significant because it's just basically a DOS protection that you don't spam the chain with transactions. So finally, we can jump to the idea of a sandwich attack. And the sandwich attack is literally, as the name suggests, is you have some toast like from an adversary, like a transaction A1, another toast or bread on the other side, and in the middle you have a meaty juice, the meaty beef that you can eat in a sandwich, right? And that's the victim that you want to squeeze as much as possible, or you want to squeeze out the financial liquidity as much as possible, meaning you want to maximize the victim slippage such that you actually reach here the slippage limit of the victim, but you don't cross it. You don't want that the victim's transaction fails. And this precisely is the concept of a sandwich attack. And to go back to the topic of today's talk, this is one of the sources of MEV, or blockchain extractable value, that you can find on chain, and it's being practiced quite significantly in nowadays systems. So how much are we talking about? What's the size? So here I will proceed now to show you a few figures. We have quite a few exchanges that we looked at. So Banco, Uniswap version 1, version 2, and SushiSwap. We indicated here when the respective exchanges launched. And you have a timeline on the x-axis and a logarithmic profit on the y-axis in US dollar. And so you can see it's been growing quite a bit in recent months here. Same here for the I mean, this is basically the attack profit in USD, and here this is the monthly number of attacks. So we try to also isolate the individual numbers in this particular example. So you can see here Uniswap version 2, for example, in this particular month, this was September 2020, achieved actually got quite a lot of sandwich attacks itself. So now regarding liquidations, so if you look at liquidations, we can see here that we have an accumulative profit of liquidations up to, I think this is like end of 2020, of up to $20 million US. And here we have the number of liquidation events. So I have to note that we excluded some of the liquidation events, for example, of MakerDAO, because MakerDAO is an auction mechanism that takes a little bit more time to develop, whereas fixed spread liquidation events are like single transaction liquidation events. Therefore, they're much easier to extract from a miner perspective when miners are extracting liquidity. So these are just some numbers for liquidations. Now, what about arbitrage? Well, arbitrage is, again, we looked at a variety of different exchanges here. We even included like stablecoin exchanges such as Curve, and you can see there's quite a significant volume in arbitrage. But again, you can see here that there, I think it's SushiSwap and Uniswap version 2, which are the most active exchanges where arbitrage is being performed. I would refer you to our paper for the metrics that we use to identify arbitrage specifically. Now, these are the three sources of blockchain extractable value that you can for example, quantify on chain. There's a like a fourth category of blockchain extractable value that we named transaction replay. The idea is really that you just copycat and replay a transaction. So you observe a transaction on the network layer of the blockchain, you replace certain data, you package it in your own transaction, and you broadcast it. Right. So this is literally a replay or copycat attack. So we found that with a very simple algorithm that I will show you on next slide, where it was possible to generate like a potential profit of about $35 million US. I'm telling you that this is a potential profit because we did not execute this one. So this is a hypothetical profit by replaying past historical blockchain data. So there might be other hiccups like other people replaying you or other issues or other front runners. But this is purely based on a historical blockchain data replay. We find that about 0.02% of all transactions within these 2.5 years are replayable with the simple algorithm, and And our algorithm is so simple that it actually does execute in near real time if you consider the speed of regular blockchains like Ethereum. So what is this algorithm? How does it look? Well, it's really just these few lines here that you can see in algorithm 1. So what we really do is we replace here the sender with the adversarial address, and in the transaction if there's a transaction input, we search if there's the original sender, and if there's the original sender in transaction input, then we do replace it as well with the adversarial address, and that's it. This is literally everything we do, right? So we literally just try to replace the sender address, and we search in the transaction input data whether there's the sender address as well, and we replace it. So it's a very simple algorithm, as you can see, but it actually would have generated some financial revenue if you would have executed it in the past. So just to show you how much revenue you could have gotten, we plotted here the following figures. So again, this is the profit and the number of replayable transactions. And what's interesting here is there's quite a spike in revenue. I think this was the BZX attack, if I'm not wrong. I think you can correct me here. So actually such algorithms might have captured some attacks at times. So imagine you see there's an attacker out there who's trying to exploit a DeFi protocol. All you run is the simple and really dumb transaction replay algorithm. And then for some reason you might actually front run an adversary, because this algorithm does not require to understand the victim transaction's logic or anything about the transaction. Sorry, this is a generous front-running algorithm, and it does qualify as blockchain extractable value because a miner could just apply such algorithm on each block that is being mined. There's a question in the chat. Okay. Let me know if you like to raise.
Arthur, right. Not really. Can you have 2 minutes to conclude, if possible?
Yep, that's perfect. So just a last note. So there's BEV is a danger to the blockchain security. So we found that for example, there's example numbers. For example, 10% miner. If you have an MEV opportunity that exceeds 4 times the block reward, then this 10% miner is incentivized to fork the chain. And that's terrible, because we found BEV opportunities that are over 800x the block reward, right? So this is really, this is critical, because then the miners are incentivized to create their own realities, their own forks, which is very detrimental to the security of the chain. Last note, so how can we mitigate MEV or BEV in general? So this is the last slide. This is ongoing work and future work, on which I invite you to join in, because it's a very exciting topic. There may be techniques on fair ordering. You can try to fix MEV of existing dApps. You can try to design MEV mindful dApps, but all this might still be not perfect, and it might not even fix cross-chain MEV. ... So with this, yeah, I would like to leave it up to you, and I'm happy to take any questions.
Yeah, thanks a lot, Arthur. So I'm moderating. We don't have many questions. So Daniel Libo has a question. Daniel, would you mind asking your question? You can talk now. I've allowed you to talk, so you can directly ask your question if you want.
Awesome. Thank you so much. Arthur, thank you. Can you hear me?
Yes, we do.
Yeah, okay, cool, excellent. Arthur, thank you so much for this presentation. It's really fascinating. I think MEV is really a bit of a roadblock for broad adoption of any smart contract platform. I really see it as a bug and not a feature. You know, who in their right mind, whether entrepreneur or large corporation, will want to be systemically cheated on, right? So therefore, I have this question. I know it's a little bit difficult of a question to answer, but I still want to use this opportunity. How would you design a consensus algorithm so that MEV is either much harder than on Ethereum or even impossible? Do you have any views on that?
Right. I mean, the beauty about DeFi is that like everything is kind of intertwined across layers, right? So I wouldn't want to isolate the solution space to just the consensus algorithm, right? I would like to look into the network layer, the consensus algorithm, the application layer, consider them all together, right? In kind of like as potential fixes, right? Because this is where issues arise, right? On this interdisciplinary construct, in essence. But one avenue is this fair ordering, right, on the blockchain layer. So if you find a way to make sure that the entity that first broadcasts a transaction actually gets a chance to mine this transaction first, right, then you've solved the issue. It's quite complicated, and I'm not aware of any generic solution that would work for permissionless system as of now. But that's one way. And the other way of thinking about it is to really design MEV mindful dApps, right? So for example, like a price oracle update in a liquidation and lending system can actually perform the liquidation, and it can pay out the profit to a wide variety of token holders, for instance. And it's possible to do so without any, or with let's say with less overhead on the underlying chain in terms of network layer overhead and blockchain overhead because of blockchain extractable value. I mean, so we feel there are avenues. It's not going to be an easy fix, and it's going to come at some cost in some instances, and yeah. I feel like there's a wide variety of possible fixes to protect users and protocols in general.
Thank you, Arthur, and I'll be in touch on LinkedIn.
Very good.
Okay, cool. Thanks, Dan. Since there is no question, well, they are coming in, but I had a follow-up question, so maybe I will ask it. So I think it's related to what you were just talking about. What do you think of the Flashbots initiative? I think they are trying to address this, right? And a lot of the transaction now, the big transaction on Ethereum are going through their supposedly front-running resistant protocol. So do you think it's a solution or not? And if not, why not?
So Flashbots is a centralized server, right? Which has peering agreements with miners. So exactly. and the centralized server receives so-called bundles, which are MEV extracting transactions, which then share the profit with miners. In essence, this kind of like such a relayer tries to maximize MEV extraction, and maximizing MEV extraction is dangerous because it can put the security of the chain at risk. It incentivizes miners to fork, and if people say that miners are not yet forking, it's because they don't know how. But as soon as you build an optimal algorithm for them to fork, why wouldn't they, right? If they gain more revenue. And the funny thing is there are papers out there that give you an optimal algorithm to fork the chain, but nobody has implemented them yet in wider practice.
I thought Flashbot, by giving directly the reward to the miner, were killing this incentive to forks, but maybe I misunderstood.
No, because you don't know who will be the next miner, right? So sometimes you are the lucky miner.
That's true.
But then,
that's true.
But next time, right? I mean, so you might want to actually copy the other block and fork, because you want to get this significant reward. And it might be a rational thing to do, especially if the revenue is like 800x the average block reward, right?
So you're not convinced by Flashbot, I guess. Okay. I have a couple of questions. We have 1 or 2 minutes. Let's do it. Let's very quickly so that we don't eat too much time on our speakers. So I have one last question. Why some exchanges, so question from Arash, are more active or attractive for arbitrage than others? So do you think they are like typical, like some exchanges that are really more susceptible to this problem than others?
So I suppose you asked the question on the same chain, right? So if you have the same chain,
yes.
So exchanges on the same chain, then I assume that all these exchanges have the same speed, right? Because they use the same chain. And then the only differentiating characteristic of these exchanges is the liquidity. or the slippage, depending on their AMM formula and liquidity. So maybe those two parameters are relevant. It's a good question. I'm not entirely sure how to answer. I would guess it's only because of this, the slippage matters most, is what I would guess, but I think I need more thinking here to answer correctly.
Okay, so sorry, it's too short. We will have many more questions, but thanks a lot. Thanks a lot, Arthur. We have to move to the next speaker.
Hi everyone, David Shishka here. Can you all see my shared screen and hear me? So I really enjoyed the previous talk, and all this front running is a fascinating topic. I will talk about something else, but perhaps before I jumped into this, I say, you know, this is a joint work with Witold, Barney, and Tamlin, and we developed this mechanism for exchange liquidity provision as part of Vega. Vega is a project building a derivatives exchange. There are a few now, of course, that exist across the blockchain and DeFi world. So we started building Vega, or designing Vega, about 3 years ago, and we had kind of few design principles in mind. One of them is that we saw immediately that Ethereum is designed for front running, because you can pay gas to have your transaction executed earlier, even if we don't go into the nitty-gritty of actually miners, you know, doing what was being described in the previous talk. So clearly Ethereum was not designed with trading in mind, and there are problems. So Vega is aiming to solve the problems of front running. We have developed a fair ordering protocol called Wendy. The other thing that that Vega is doing is we're building a purpose-built blockchain, which is in fact running the entire limit order book on chain. And the reason for that is that we believe that limit order books are better for price discovery than bonding curves or automated market makers. It's not clear to me out in the wild that there are any AMM markets where price discovery happens. And from what I've observed, the price discovery happens on, you know, more liquid limit order book based exchanges, and the automated market makers just follow the price that has been set there. And the other thing is that Vega is designed for trading derivatives, so that, you know, changes some of the design considerations, but it also neatly connects with the previous talk, because one of the source of miner extractable value are, of course, the liquidation trades coming from protocols like DYDX. On Vega, this doesn't happen by design, because liquidations on delinquent positions are performed atomically, and we can do that because, you know, we are not building on top of a general purpose blockchain like Ethereum, but we are building a purpose-built blockchain. Okay, so enough of these general comments, and we move to talking about liquidity. So I will talk a little bit about what is understood by liquidity. It's one of these concepts that everyone likes to talk about, and pretty much everyone who's moving in this space has got some intuitive understanding. Defining it rigorously is a bit tricky, because there are many good ways of definitions for liquidity, and it's not clear that you can say that one is necessarily better than another. And then after that, I will talk about the protocol that we developed for incentivizing liquidity on derivative markets. So we found this some time ago. We found this lovely paper by Fisher-Black, who's of course famous because of the Black-Scholes equation. But it's interesting to see that even in the 70s, people were thinking about, you know, how to automate how to automate trading and stock exchanges, etc. And as part of the paper, he gave quite a nice overview of, you know, what you would want from a liquid market. So the first thing is that you have, you know, you always have bid and ask prices. In other words, you can always buy or sell at least small amount of the stock straight away. Ideally, of course, you want small bid and ask spread if you're to call a market liquid. If you want to sell large amount, you can sell it bit by bit, and you expect the volume to be replenished on the book. In other words, you know, you make a small trade, it eats some of the volume, but very quickly the volume reappears if it's a liquid market, and you can make another bit of your small trade. And you shouldn't move too far away from the current market prices as you do the execution. So that's kind of liquidity across time, if you like. And then another aspect or another angle, of course, is that if you want, you can do one big block trade, but then you suffer slippage. And if you look at for example, the AMM design, the sushi swap that was discussed before, if the pools are sufficiently big, it actually, you know, fulfills all of these properties identified here. So you know, for big pools, they provide nice and liquid markets. So why do exchanges, you know, care about having good liquidity? Well, it lowers execution costs and decreases risk for participants, so that makes them more attractive to users. It improves price discovery information flows. It encourages more sophisticated trading strategies. So you would get, you know, hedge funds and others who would trade on your exchange and pay fees, and then the exchange will be nice and profitable. But now I want to focus on the last part, which is, you know, it allows safe operation of a derivatives exchange. So trading a derivative is quite different from trading spot, because if you trade spot, you say, okay, I want to buy 2 Bitcoin, I hand over $100,000 or whatever the current price is, and the exchange facilitated the price discovery, the swap happened, and the trade is over, and the story ends for that trade anyway. If you do the same for a derivative, like let's say a cash settled future or an option or many other kind of derivatives, you know, the exchange helps you to find fair price, but once the trade happened, you effectively exchanged promises, right? You promise that you're going to keep the, you know, either legal agreement for the derivative trade if you're in the old world of finance, or you're basically promising that you're going to stay solvent so that you will have enough money at settlement time so that the smart contract on blockchain can actually provide the correct settlement cash flows. And the exchange works as a central counterparty in this trade. So it has to ensure, to be attractive, it has to have mechanisms to ensure that people actually keep their promises. And this leads to the concept of collateral and margin. So the exchange will, to place an order and then to enter a trade, you will be required to post collateral of certain margin level. There are many, you know, sensible ways you can design the margin requirements, and they depend on a number of things. I don't want to go into that, but the point is that if one of the parties can't meet the margin requirement, then there is a worry that they won't be able to keep the promise later come settlement time. And so the exchange would like to close this delinquent party out. And of course, in order to be able to execute the closeout trade, there has to be volume on the order book, and hopefully not too badly priced, so that the closeout trade can be executed, and, you know, the margin can be used to, or what's left of the margin can be used to execute the closeout trade. So for derivatives exchanges, you know, liquidity is not something that's nice to have because it attracts users, but it's an essential feature to operate a derivatives exchange safely. And so how do, you know, how do exchanges in sort of the classical world of finance arrange liquidity? It's done through, you know, complicated bespoke legal agreements that take, you know, some time to arrange, and then they're governed by laws or whatever jurisdiction they're operating in. But it's certainly not automatic, because it can be quite complex setup. So what we are trying to, or what we did with Vega, was to actually design a protocol for liquidity provision for a derivatives market. And I will use the rest of the talk to actually walk you through some of the design that we have. So sort of the principles and the overview of the design is that there are liquidity providers who will commit a financial bond or a stake to the protocol. So they will lock up some money, some collateral, and in exchange for that, they will be eligible for some of the trading fee revenue. The protocol is designed in such a way that it posts and refreshes volume, in other words, orders on the book, and this is done proportional to the stake, to the bond that they committed. The LPs must be able to choose where they post their volume, because that allows them to, you know, do their position management, because otherwise they might end up too long or too short, and that creates an unacceptable risk for them. Placing volume on the book costs margin, and if they post the volume far away from the best bid or best ask, then they have to post more volume to compensate, and so that would cost them more in margin. We estimate liquidity demand, and there is basically a fee setting auction running automatically, so that only the liquidity providers which provide essential liquidity, when you look at it, ordered by the lowest fee, are the ones who actually set the fee. So the fee is always the lowest possible. And finally, if you're the one who bootstraps a market, in other words, provides early liquidity which allows the market to grow, that somehow that should be captured in the share of the rewards that you receive. So let's now look at this in a bit more detail. So in order to, you know, ensure the market is sufficiently liquid, we have to pick one of the definitions of liquidity that are available. And what we effectively do is say that the liquidity is volume on the book, but scaled by the probability of trading. So it's just a weighted average volume on the book, and the weighting is coming from probability of trading. I'll get to probability of trading in a moment. And then, of course, you've got the sell side volume, and you've got the buy side volume, and then you say the liquidity is the lesser of these two. And then this gives you a number that represents liquidity on the book at a point in time. And as I said before, there are many sensible definitions of liquidity. This is just one of them. And you might be asking, okay, where does this probability of trading come from? And the answer is, well, if you're operating a derivatives exchange, you need to decide how much margin to charge. And if you're deciding how much margin to charge, the only sensible way to do this is to have some kind of, you know, statistical model for the likely moves of the price of the underlying asset. Well, but if you have that to calculate margin, you might as well recycle the same, you know, stochastic model to decide what are your price moves probabilities. And so you get the probability of trading simply from the density function of your price moves. So this is, you know, this is how you would measure liquidity. And what this is used for is to place volume on the order book for anyone who committed to be a liquidity provider, proportional, and then this proportional amount to the stake. So the stake that they commit basically commits them to posting certain amount of liquidity. And so how this works is that the exchange implements effectively special type of order, which is, it's not a limit order, it's not a pegged order, it's a special liquidity provision order. And what happens that as part of this order, you specify how you want to have your volume distributed. So you can say, you can see these thin blue lines here, they're visible better, but they're also sitting here. So you say, okay, nothing from mid until 125, and then all my volume will go uniformly from that point, until 100.5, and then you can do something different on the bid side. You can also have some limit orders here. And here they're the dark colors, the dark green and dark red. They're sort of entered into the liquidity calculation. And if you're providing enough liquidity according to the liquidity formula I've shown before, then this special liquidity provision order will post nothing on the book for you. But if it's not quite enough, then it will post volume according to the distribution you've put here. And of course, because the probability of trading here is much higher than the probability that the price will move to 105 in the next time step, whatever you decide the sensible time step is. Here, the volume that this order posts on the book for you is much higher. And because the volume is much higher, you'll end up paying noticeably more in margin. So as a liquidity provider, you sort of have to balance, you're paying the game. Either I post my volume closer to the best bid and ask. If I do that, then my orders are more likely to trade, which means that I'll have to be, more active in position management, and this might incur costs. Or I post the volume further away, but that increases significantly the margin cost, so I've got more capital locked up, and it's up to you how you decide to balance this conundrum. You can devise a number of market making strategies that make you happy as a liquidity provider, and then for the capital that you lock up, you get a share of the fee revenue. So how do we actually set the fee? So we say that we don't want people, traders, to pay for liquidity that they don't need on the market in the form of potentially higher fees. So the first thing we have to do is to estimate the liquidity demand. And again, there are many ways in which you can sensibly estimate liquidity demand. The view we take in Vega currently is purely based on the concept that we are trading derivatives. I see someone raised the hand. Would someone like to ask a question?
There is only one question in the Q&A.
So yes, we were supposed to take them at the end. You want to take it now? Okay.
I'll just answer this one now, since I sort of stopped. So the question is, sorry, I'll let Ifan ask. I'll let Ifan ask directly.
Yeah, I have to allow her. Ifan, do you mind speaking? I think I've allowed you. Or not? You should be able to speak up, Ifan, if you want to raise your question.
Yeah. Can you hear me?
Yes.
Yeah.
Yes.
Oh, yeah. Thanks. So I posted my question in the Q&A box, but I think I'll ask it right now. So you mentioned just now that the liquidity providers, in this case, is able to adjust the shape of their quote distribution, right? And let's assume that the liquidity provider is some intelligent people that want to make a profit. So if this liquidity provider wants to adjust the distribution of his quotes on the chain, right? How much time can he expect this adjustment to take effect? And will this adjustment incur a fee for the?
Yeah, so that's a great question. So Vega is running its own blockchain. The consensus layer is based on Tendermint, so that's a proof of stake protocol, not proof of work. So to change the shape, they basically submit a, an update to this order, if you like.
Yeah.
For the consensus, for the gossip to happen, that is, we are currently looking at 1 to 2 second block times. So that might take 1 or 2 seconds for their order to actually go in, be agreed by all the nodes, and then processed by the core. And it does not incur any fees because we don't have anything like gas costs. I mean, in fact, on a blockchain that's optimized for trading, you wouldn't want to charge fees on orders because orders give you information about price and about what is happening. And exchange is one of the primary purposes is price discovery. So not charging fees on orders is important. So that there is no fee charge on the order. So they can adjust this with a frequency of 1 to every 2 seconds, every 5 seconds if things are slow and congested, but very frequently. And in the meantime, so it's a great question because our initial design was that they post limit orders, and if they don't meet their commitment, they'll be penalized. And then we thought, well, that's a bit unfair. If the network's congested or they can't post because their internet connection is down for a few seconds or whatever, we don't want to penalize them. So then we said, no, the protocol itself will refresh the orders for them, but they can change how they're shaped.
Okay. So the quoters actually lose the ability to control exactly where they quote, but they give you this generalized shape, and then the algorithm will automatically adjust.
Yeah, so they can say exactly how far they want to be from places like mid or best bid or best ask, and then as things move around, the orders will be pegged to the whatever peg they chose. So let's say best bid.
Yeah, thank you very much.
And then the volume will change automatically.
Oh yeah, that's great. That's clear. Yeah, thanks a lot.
Thank you. So yeah, so going back to the liquidity demand, we just set it to be related to open interest. The reason for that is, if you have a very simple situation, 2 parties traded on the exchange, one took the long position, one took the short position, the open interest is exactly 1. And so that's the maximum closeout trade that you would ever want to possibly do. So somehow it seems natural that you relate the liquidity demand on a derivatives exchange to open interest. And that's what we do. So the stake related is effectively related to this, is directly proportional to this liquidity demand, and it's scaled by mark price and the risk factor. The risk factor is something that determines margins, and the mark price is just to convert, this open interest to a monetary value, because the stake is now an amount of money that that the exchange is saying, this is how much stake I have for, this is how much stake I would like for safe operation. And the reason to include the risk factor is that we're using the bond, the stake of the liquidity providers. If they can't meet their margin requirements, this stake will be used to meet the margin requirement for them, so that their positions can stay open, so that they're unlikely to they themselves become a reason for why liquidations happen on the exchange. So that gives us the concept of required stake. And right, I jumped the gun a little bit. Yeah, so the committed stake is transferred into the bond account. They can increase the amount of stake that they put in their liquidity provision at any time. They can decrease it if the exchange feels that there is enough stake provided by others, so then they can escape their commitment. Otherwise, it's locked till the market settles or till the liquidity demand drops. And if they can't meet their margin requirements, this collateral in the bond account is used, and a small penalty is applied as well to sort of disincentivize such behavior.
Could you please wrap up in 2 minutes, David?
Yeah, thank you. So I just realized I think I've lost a slide on the fee auction. So effectively the way the fee is set is that you order all the commitments, and the fee bids that the liquidity providers submit, you order them from the smallest fee to the biggest fee. And then you're summing up the stake that they're committed till you just pass the required amount, and then you take the corresponding fee bid, and that's the fee that's being used in the market. So it's the lowest possible one that satisfies the estimated liquidity requirement, which is proportional to the stake requirement. And the last part is that I was saying that effectively, if you bootstrap a market, if you're the first one who provides liquidity and you take more risk because it's a market that might not trade and you lock up your capital to something that's not going to make you much money, you should be rewarded more than someone who comes into a liquid market. And so what we do is effectively we estimate the market value, where the market value is just effectively the volume traded over some period of time looking back, and then from that increasing your stake or adding new stake if you were not a liquidity provider yet works a little bit like buying a share in this market. So that's what these formulas do, but I think a picture might be easier. So this is traded volume from, I think it's Ethereum futures from FTX, but it doesn't matter. You've got traded volume. The valuation is basically a glorified moving average of the traded volume. And then here we have a situation where let's look at the stake first. So initially I've got the red and green guys had 0, and these two, blue and yellow, bootstrapped the market. So initially they have the equity share is proportional to how much they committed. Then the green guy entered, but you see it was they entered at a time when the market was already quite valuable. And so even though they're providing more stake than both the blue and the yellow guy, they're actually not getting that much on the equity share on the equity share measure, and similar thing happens with the red guy who enters even later, that they pay so much that in terms of stake that they're at 80%, but in terms of how much of the equity in the market they only have about 50%. And then the fees that are collected from the trading are distributed proportionally to the equity share, not actually directly proportional to the stake. So that gives you the concept of whoever grew the market gets disproportionate rewards. And then I realized this talk might have been a little bit quick, so you can find these papers and other papers on the Vega website. We have the more detailed specifications for the protocol on GitHub, and we have a testnet running, and it's been running for a while, so you can give things a shot there as well, though it's a testnet, so your mileage may vary. Thank you.
Hi, thanks, David. So we don't have much time. I have a question in the chat, find the Q&A box. A question for Bernard Meister. He's asking whether ignoring the liquidity outside your exchange seems wasteful. Do you agree with the statement or disagree?
Well, it's how things work. It's how things are, right? I mean, there are exchanges, then there is scope for protocols that actually route orders to the best exchange, etc. But you know, on some level there has to be exchange, and yes, there will be liquidity outside this exchange. That's how things are.
So you don't feel too much competition of order routing, aggregate order routing, like yeah.
I think that you know, order routing is a valuable service, and it basically routes orders to wherever they can be best executed. And your only hope as someone who's, you know, designing an exchange protocol is to design one where, by the virtue of its design, it'll be the most favorable. So, you know, the least slippage or the lowest fees or the fastest execution or not being front run. And we're hoping that our protocol ticks enough of these boxes to make it, you know, make it to the top in order routing.
I agree. So another question by Dan Libo. So he's wondering whether all products on your exchange will be issued by the exchange itself.
Yeah, so that's a great question, because it gives me an opportunity to talk about another aspect. So the product at the moment that's coded up are cash settled futures. We have a design to allow a product design language which will allow you in the future to write down any kind of, you know, derivative payoff. And we also allow anyone to launch any kind of market, and that's just subject to the community vote. So you propose a market, at the moment it would be cash settled future. You can propose market that pays, you know, dollars based on how much rainfall there was somewhere in the world. As long as you can provide an oracle, you convince the community that the oracle is good, they vote the market into existence, it will start trading.
Okay, thanks a lot for your answer and your presentation. Unfortunately, we have to move on. We're already out of time. So last presenter, Jae Wong, it's your the screen is yours. Looking forward to your presentation.
Okay, thanks. I really enjoyed the previous two talks, so now it's my turn. Let me introduce myself. I'm Jae Wong. I'm a PhD student from ETH Zurich. So I'm very happy to be invited to give the talk on our work, Cyclic arbitrage in decentralized exchange market. So let's start from the very beginning of the cryptocurrency ecosystem. So at the very beginning, the cryptocurrency ecosystem is just a peer-to-peer electrical payment system that allows people to transfer money from one account to another. But however, with the development of the whole ecosystem, we find that there are not only just one single token there are a lot of different tokens, or even we say like more than 200,000 tokens there. So then there's people have the demand to exchange their money with each other. So for example, if the left guy wants the USDT, but the right guy wants the Ethereum, they have to find a way to exchange with them. But the hard thing is that if we just do it on-chain, it's hard for them to find another user who also wants to do the exchange. And also it's hard for them to determine the price. And also it's hard to ensure that the exchange happens successfully at the same time. So what people usually do is that they usually use the centralized exchanges. They just send their money to a third party and exchange their money within the third party. And everything of this exchange between tokens happens off-chain. So there's the issue of this kind of traditional centralized exchange market of the cryptocurrency is that everyone have to send their assets to this third party, and the third party control all of their money. And also the trades that they have done in this centralized market is not visible. So in such a case, people consider to move from the centralized market to the decentralized market. So when we say decentralized exchanges, they are just smart contract on the blockchain. So now if a trader want to exchange money with another people, they just need to send the blockchain transaction to the smart contract, and smart contract will execute their financial operations. and all these financial operations will be recorded on the blockchain. So the good thing is that the traders, they always take control of their own asset. They're not sending the money to a third party and trust them, but they can always keep it in their own wallet. So there are several different mechanisms of these decentralized exchanges. So some of them are just use a very, traditional market mechanism similar to what happens in the, financial market like the stock market or other market. They use the order marching mechanism. So in such a case, when trader want to buy the USDT, he just sends the order to the smart contract, but he cannot immediately get the USDT he wants, because if in the market everyone wants a USDT, then no one will trade with him. He can only wait until another trader who wants to sell USDT, and then this exchange execute successfully. And even worse, maybe other people can provide a better price with the guy who first come to the market. So then this guy will eventually have to wait and wait and wait. And we don't know that when his transaction will be executed. So in such a sense, the DeFi community come up with another idea, is a automatic maker mechanism. So in such a decentralized exchange market, someone just reserves their money in a smart contract in advance to all the transaction happens. So for example, in this, in this example, we call the liquidity provider. He just put his Ether and the USDT into a smart contract, and we call this smart contract liquidity pool. So when there is some money in the liquidity pool, then traders can easily just make transaction with this liquidity pool smart contract. So for example, now if the trader wants to buy USDT with 20 Ether, it does not need wait until some other people to also have the transaction order from the opposite direction. He can directly get the USDT back from the smart contract. So another interesting in this automatic market market maker decentralized exchanges is that how to determine the price. So normally people just, one not very popular pricing mechanism is called constant product pricing mechanism, is that before the trades and after trades, they want to ensure the product of the reserves in the smart contract always keeps the same. So for instance, in our example, before the buying USDT trade, there's 100 Ether and 300,000 USDT in the liquidity pool, and the product is 30 million. And after the trade, we also keep 30 million USDT times Ether in the market. So then what we found is that actually this trade changes the exchange rate in this market. So before this trade happens, the exchange rate between the Ether and USDT is 3,000. But after this trade happens, the exchange rate between the Ether and USDT is come to 2,000, which means that every trade, which means that the price of the market is determined by the liquidity, and also every trade can change its price. So as we say that some people just put their money in this liquidity pool and allow others to do these trades, automatically. But the problem is that what the benefits they can have from providing such, basic infrastructure of these decentralized exchanges is that they can get a commission fee from the trades that happens in this liquidity pool. So for instance, let's come back to the example that we just showed. If this guy wants to buy USDT with 20 Ether, actually, he cannot really trade this 20 Ether with the market. So for example, in the Uniswap and the SushiSwap, they will take their 0.3% of the trades as a commission fee. So in particular, this guy can only trade 19.94 Ether with the market. And also similarly, he cannot get 50,000 USDT back. So the amount of token he can get is just 49,875 USDT back. So far, we only show that the trade between two tokens. But as I mentioned, that there's more than 200,000 tokens in the market. So we can expect that it is possible between any pair of tokens, there can be a liquidity pool smart contract, and there are thousands of the exchange market in the blockchain ecosystem. So for example, if we have 4 tokens, Ether, USDC, USDT, and Bitcoin, we can actually have 6 markets in there. And the thing is that, as we said, the exchange rate between these tokens are determined by every individual trades, and also determined by the liquidity in the smart contract, which means that they are almost independent in the market. They are almost independent with each other. So in such case, we can almost assure that the exchange rate across different markets are unbalanced. So here we take a snapshot of the market state in October of 2020. Then we can see that if the trader want to exchange USDT with Ether with Bitcoin, and the Bitcoin with USDT again, the exchange rate between his input USDT and output USDT is actually 1.002, which is larger than 1. This suggests that there can be the opportunity for people to get benefit from these cyclic arbitrages. So motivated by this zero result, we really observe there's a lot of cyclic transactions in Uniswap market. For example, this is a transaction happened on the end of October last year. We see that what the trader do in this transaction is that he just trades 280 USDC with USDT in the liquidity pool and get 283 USDT back. And then he used all of the USDT he gets from the previous trades to exchange with a seal. And then he get 2 seal and exchange to 1.5 KP3R. And then he used all the KP3R he gets to get USDC back. So at the end, I mean, the previous example just shows the exchange rate can be 1.002. But in this real implementation, what we can observe is that he used 285 USDC and gets 300 USDC back. So in our paper, we studied these cyclic arbitrages theoretically. What we try to solve in the paper is that we find how can we determine whether a transaction is profitable. We find what is the optimal revenue that people can get from these cyclic arbitrages. And we also study what's the influence of the cyclic arbitrages to the market state. But because some computation is quite complicated, and also we do not have any time today, so we refer people who are interested in this theoretical topic to read our paper. So then, now we understand the theory. We understand when the cyclic transactions is profitable. We know that how can we get maximum profitable in the market. So then, can we really do this in Uniswap or in other decentralized exchanges? So to answer this question, we look into the practice. We look into the real world data. So we collect our data with the Go Ethereum client. So this is a client provided by the Ethereum Foundation. So with this client, what we can have is that we can have all the transaction information on the blockchain. So as I just mentioned, is that for the decentralized exchange, every trade is recorded on the blockchain. So what we look into is specifically the sync event. So when there is any market operation happens on the decentralized exchanges, for example, like on Uniswap, the smart contract will generate a sync event and to update what is reserves in the liquidity pool smart contract. So if we just look into all the sync events, we can understand that how this reserves changes in the liquidity pool over time. So with such information, we look into a real block. We look into we look into the market state of the block in January 2021. So then we measure that what is the arbitrage opportunities at that time point. So in the picture that I show here is that we just show the distribution of the arbitrage opportunities by the end of the January. So the XXL is the optimal profit that people can get from the cyclic arbitrage strategy, and the YXL determine what number of the cycles that people can get such of the profit. So you should notice that for our YXL we use a log scale. So which means that actually there are a lot of potential arbitrage opportunities in that block. So actually, out of 3,700 triangles in the Uniswap V2 market, we find 1,400 triangles can be profitable. And here we show that. I mean, in the previous example, we showed that the profit is only $20, but here we show that there are even some arbitrage opportunities have a potential revenue higher than $200. And this is not all of them. There are also 8 outliers, which is much, I mean, the profits that they can provide is far beyond the rest of them. So we can see that with these cycles, with Ether, USDT, and USD 3 cryptocurrencies, people can actually get 22 Ether from this simple cyclic transactions. Another thing that we should notice here is that we find that for these cycles, actually there's some of them are used the same liquidity pool. So for instance, here they are for the top 5, I mean, cyclic arbitrages, they all use the Ether and USD, I mean, liquidity pool, which means that maybe it is impossible for us to get all of this profit from by cyclic transactions, but it's still that there's still a lot of potential opportunities there. So then we also measure what is the sum of this cyclic arbitrage opportunities in the market. So here what we show is that XXL is a time frame from the May 2020 to January 2021, and the YXL is the number of the arbitrage opportunities that we find in each block. So we find that almost in every block, with the development of the Uniswap, or we say the blockchain ecosystem, the potential arbitrage opportunities are very, very huge. And also similarly, we measure what is the profit that people can have from this cyclic, from doing these cyclic transactions. So the XL in this figure is also the time frame from May to January, and the YXL is the sum of the profits that people can have from these potential opportunities. And we find that they are almost stable at 100 Ether per block. So although that we know there is some conflict between some arbitrage opportunities, but I mean, on average, the profit of the single transaction can be like 0.1 Ether, which means like almost $300 US. So which still suggests that we can do a lot of cyclic arbitrages in decentralized exchange market. So now, until now, we're still talking about what is potential opportunities here, but how should we do? How can we really make these potential opportunities to real profit? So the next part I'm talking about is implementation of cyclic arbitrages. So the very naive idea is that we can just do these trades, I mean, sequentially. So for example, with this free market, we can just first exchange the USDC with Ether, and then Ether with USDT, and then USDT with USDC. And ideally, we will get what we want. But unfortunately, because we do these transactions one by one, it is also possible that some other trades happens in front of us, happens before our, market operations and change the market price. So this price impact should be also considered in this cyclic arbitrage implementations. But the good thing is that in the blockchain world, it's not like just in some foreign exchange world, which also, cyclic arbitrage is possible. In the blockchain world, people can use a smart contract to make sure that what they want, what they get is exactly what they want. So in this, if they use a smart contract to implement such cyclic arbitrages, they do not directly do this, swap between two tokens, by themselves. They just give the money to the smart contract and let the smart contract do the 3 swaps. And after that, the smart contract can check whether the output of the USDC is larger or at least larger than the input of the USDC. So if it not, which means that if the implementation of the arbitrage is not profitable, then the smart contract can be reverted to the previous state, which means that the trader do not need to take the risk of the losing money from these cyclic transactions. So we also try our idea of this transaction. We also have the implementation of these ideas. So if someone are interested in how to do this, we call it atomic implementation, you can refer to this GitHub, and this is also public. So the next thing that I want to discuss is what is the difference between the expectation and reality. Because until now, everything that we discussed that, okay, there's a lot of opportunities there, and we can easily to exploit these arbitrage opportunities. But what happens in reality? Are people really doing this? We also get the data from the Go Ethereum, but this time we focus on the swap event. The swap event is that every time when people trade and make a transaction between 2 cryptocurrencies, there will be a swap event recorded in the blockchain system. So with this swap event, we can know that which 2 tokens people are trade with and what is the input amount and what is output amount they're trading. So then this is cyclic arbitrages that we find in the market. We find the XL in this figure is the time frame, and the YXL is that the numbers of the cyclic arbitrages in per day. So we find that the market is growing immediately after the emergence of Uniswap V2, and until by the end of the January, we find almost 300,000 cyclic in total. And also, we measure what is the actual revenue that people can get from the market. In this figure, XL is the time frame from May to the January, and the YXL determines the revenue, and the black line determines what is the daily revenue that arbitrageurs get from the market, and the orange dot line determines what is the accumulated revenue people have in the market. And the Y scale is in log, Y-axis is in log scale as well. So we can see that the market is gradually increasing, and now, by the end of the January, it's a kind of stable, and which means that people can, continuously get money from the cyclic transaction strategies in the market. So I'm almost around on time. So have I finished it? Actually, no. So we also do something else, but because of the time constraint, I just skip this part. So if you are interested in how we evaluate the real implementations in the market, you can go into, you can read our paper, and there's more details about it. Thanks for your patience. That's all for my talk today.
Thank you. Thanks a lot. So we have a couple of questions. So another question from Yifan. What do you think about the interaction between centralized exchanges and the DeFi liquidity pools?
As I said, that for the centralized exchanges, that your money is controlled by the third party, and you have to transfer all your money to them before you do the trade, which means that you must trust them.
But I don't think Yifan is talking about comparing centralized exchanging and DeFi, saying that right now we have DeFi liquidity pool and centralized exchanges that operate at the same time, no? Over the same type of pair. So what type of interaction do you see between them?
Actually, there are two systems. Not, I mean, as I said, centralized exchanges are not happens on the blockchain. So exchange in centralized exchanges are off-chain, but trades of the decentralized exchanges are always on-chain. So these are two systems are separated. So if you want to do the interaction, you must go through the third party. And
but you could have arbitrage, or you also have arbitrage between prices in centralized exchanges and decentralized exchanges. I guess that was more the idea of the question. Now, I have also a question from Ganesh. Maybe Ganesh, you want allow you to talk. Maybe you can raise your question yourself if you want.
Yeah, cool. Thanks, Julian. Yeah, so I was just curious about the triangular arbitrage. So for ETH, USDT, USD, you've got an ETH USDT pool, and then a USDT USD pool, and ETH USD pool. Is that right?
Sorry, you mean the example that I show with the highest revenue, or?
Yes, exactly.
Yes, it is for through these three pools.
Okay, so I guess I don't know Uniswap too well, but do you have USDT USD liquidity pool on Uniswap?
They have the USDT and the USD liquidity pool.
Okay, because I thought that you could not get USD.
This USD is not the fiat money. It's a cryptocurrency called USD.
Oh, okay. But is that a stable coin as well?
It is designed as a stable coin, but we don't know how it looks like now.
Okay.
Because this happens on October, not on January, sorry. So maybe, I mean, you know, the crypto world, I mean, changes so fast.
Yeah. I mean, the fact that all the highest revenues involve this pair, I guess I was thinking, is this pair like kind of like, I guess, a token that's sort of fluctuating in value a lot, or I guess it seems like all of these high revenue ones are coming from this token as one of the three currencies.
Yes. So as I said, this is just a snapshot of one block. So here we can only see this token, but as I also showed there, I mean, the potential revenue is always high, so which suggests that it might not only be this one token. I mean, this can happen on any other tokens as well.
Okay. And yeah, I think the other question was also the same, as in what kind of differences between sort of across exchange versus within exchange. So I guess I was just curious, like, do you think the arbitrage or like the profits you find with Cyclical would be even higher than profits from a cross exchange, so between, say, Binance and Uniswap?
I mean, for this part, it's hard to judge, because the thing is that for centralized exchange market data, actually, it's hard for us to identify who are they, right? Although we can find, okay, there might be some opportunities there, but we don't know how people to implement it. But for looking to the decentralized exchange, the good thing is that we can really know people are doing cyclic arbitrage. So I think this is the same thing for the foreign exchange or other traditional market as well, is that we know there's a price difference, but our arbitrages really using it. And with this data, but with the decentralized exchange data, that we know who are using it, how they are using it, which opportunities they are using. So they can help us to understand more about the rationality of these traders, of these arbitrageurs in the market. So I agree that we can also do these arbitrages with I mean, between centralized exchanges and decentralized exchanges. But then, as I said, it's hard for us to identify how, I mean, what is there real activities there or something similar?
Okay, thank you.
So we have, thank you. We have another question. I'm gonna raise it myself because it's very short. It's more of a tech question, not question. How did you convert your raw data from Go Ethereum to something readable? Example, USD value.
Sorry, can you repeat that? I don't get that.
So let me say it again. You can see it in your Q&A box too. Huh? How did you convert your raw data from Go Ethereum, for example, the value of a transaction, to something readable, example given USD value?
Actually, what we measure is that we always use Ether as a
it's true. It's true.
We do not consider US dollar value because it always changes. So, and actually, all the data that all the numbers that we show here is we only measure the, I mean, the cycles or the triangles related to the Ether. Because
it's just a very small portion of the potential arbitrage. It's everything. It's going from Ether going back to Ether.
It's going from Ether and also going back to Ether, because when we say cyclic, because there's a cycle.
You can go from Ether.
But I mean, this already take the majority of the market. This is also what we have measured. That's why we only consider Ether to show this revenue thing.
Yeah. Okay. Super. Yeah, great answer. Yeah. Thanks. I don't see any other questions. Someone wants to raise among the. Anyway, so let's say that. So it's, I mean, a good point in time because we have reached 1 hour and a half. So we call it a day. Thanks to all of you for attending. Since we are not constrained by time, we will leave the chat and we can stay here to discuss. And other attendant, I mean, of course, you can leave. And if some of the people in the audience wants to join the panelists, they can raise their hand and we can make you panelist and you can talk with us for a little while.
Just before that,
thank you,
Julien.
Sure. Yeah.
We need to announce the next webinar on October 7th, which is hosted by Fahad Saleh, Professor Tim Garden from Columbia University will talk about transaction fee mechanism design. So stay tuned, and thanks again to all three speakers for very nice presentation and all the questions that we had to